Okay, hello everybody, welcome back. Hope you had a good weekend. It is hot out there. It wasn't hot over the weekend, but it's hot today, which is kind of weird. It's like 100 degrees out there. You guys probably used to it, I don't know. It's just our native California people who are going, it's hot outside. Alright, so we're going to finish up lecture number 6 today on collections, and then we're going to move into I/O and input-output streams and strings and all sorts of nifty things like that, and exception handling. We have pretty much covered after this lecture all of the object-oriented stuff. Believe it or not, that's the entire object-oriented concept which I've given you so far. The next assignment is going to be on swing and GUI stuff, but we're not going to cover that today. Instead, Wednesday-ish, maybe Monday, depends on how far I get today. We'll start in with swing and GUI development with all the GUI components and stuff. And your next assignment, number 4, is on creating a notepad program, which is pretty easy. A little drop-down menu, a little screen. It's using all the swing components or the AWT components, and I'll talk about that. And then the one after that is the easy one. No, actually, it's a more complicated object-oriented program. So all 5 programs you should be able to finish at this point, theoretically. You know, if you had all the time in the day to do it, you would be done already. All right, so I know my clock is a little bit off here because my clock says it's 9:35. So someone tell me when it's what time is it now? 5 something. Somebody tell me when it's 6:30. Could someone do that for me? When it's getting close? Okay, good. Otherwise, I have no idea what time it is because there's no clock in this room. All right. So let's talk about Java. Talk about everything else. Let's talk about Java now. Collections. I'm going to start from the beginning of this lecture, although I did get through 1 or 2 slides, just to refresh your memory because it has been a long weekend, and so, or it has been a weekend, so you may not necessarily be thinking about Java all weekend. So here we go. The concept it comes out of, and we looked at examples last time. We looked at tons of examples, and they all use the same package. It's Java util. It has everything inside of it. It has all of the collection packages. It has everything that you're going to need. So these are data structures that are supported by Java that kind of automate the process for you, so you don't have to do it yourself. And actually, a data structure is nothing more by definition than an object that holds other objects. So it's putting stuff inside of objects for easier handling, and we call those collections. And the collection framework, which is part of the big picture here, is broken into 3 different categories. Category number 1 is the collection. Category number 2 is maps, which, you know, you don't have that many applications that use maps, but you do have occasionally, you know, something that comes up. Well, when are you going to use a map? Well, if you're doing a GPS program, maybe, you could do a tree, which is a form of a map. You could do a dictionary lookup type of data structure that holds keys and values. You could do, I don't know, anything that has associations where you have multiple pieces of data that go in. So let's say one list would have multiple items that are associated with it. But most part, you're looking at this collection category where you got sets and lists, and usually 90% of the time you're going to create a list out of it. Whether you use it as a sorted collection or not, you may not, but you're still going to create a list out of it. Because the traditional data structure from most programming environments, the array, is sort of the list. So that's where we get that from. And then we have over here on this right side, we have the iterator. The iterator has the iterator list iterator. That's a special type of iterator, and we learned last time that the iterator does nothing more than allow us to go through, traverse through the list and or the collection, and go to next, go to next, go to next, so that we can find items in the collection. And we looked at these actually last time. We looked at them in a programming syntax. In fact, if you haven't, you can download the file. I showed it last lecture. I showed you where you could download it from, so you could actually load it in. And you're going to need this. Well, you might need this. You may not need this to do your stack and your queue for the assignment number 2 or 3. 3. Okay, good. Yeah, 4 is GUI, 5 is object-oriented. Yeah. So I'm going to skip through the methods because you're not going to memorize it. You're not going to know anything about looking at these methods on a PowerPoint slide. You're going to have to try them out and look at them. The iterator. The iterator's got the next, has next, remove. You remember we saw that in a couple of examples. And we are using the iterator method that's implemented by the object. And we make a new iterator from that. So we run the iterator method on the object, and the object is of a particular abstract type. It has an implementation, hopefully, for the iterator. And here's the classical routine of using the iterator IT, and this is what I'm talking about. We're running a method iterator on the collection object, and the collection object here is what we're taking in from the parameter when we run this method. And it's going to do a, IT, which is the name of the iterator object, dot has next. And has next, like sort of a loop. So no more for loops, long story short. If you're familiar with that in C or C++, you don't have to worry about that in Java. Then we have the list iterator, which is a special type of iterator that was designed for lists. Well, what does that do? I can remove, add to the top, add to the bottom, remove this, remove that, set an item in the list. So it works with the order instead of just a generic collection, so just instead of a generic grouping. We got through this part looking at problems. We got through this part. I talked about exception handling a little bit, but didn't mention it. So today I'm going to actually have a full PowerPoint on exception handling for you. Let's see, what was this? I think this is probably where we stopped, I think it goes about right here, actually. And then I said, oh, list, let me just show you one. And then I dropped out and I showed you a list. Okay, so this is where I'll pick it up. So in concept, and his is basically, I've gone through most of the stuff with programming examples. However, this is the textbook material, the concept. So because you're going to have, is there a midterm for this class? I think there is. When we're all done, I'll take a few minutes. So remind me at 6:20 instead of 6:30. I'll take a few minutes and go through the assignments, because at this point you should be thinking about doing some of this stuff and getting caught up. I know that we have 5 programming assignments, or do we have 6 of them? 5 of them. And they're worth like 5 points. Not that much. It's only 25% of your grade. We have a midterm, we have a CSLO essay, then we have a final exam. Much more than these 5 assignments. Although these 5 assignments is your learning opportunity. So I downloaded everything and I kind of got organized myself, so I'll help you get organized when we're all done, but I'll wait till the end. Okay, the list. The reason why I'm mentioning that actually is because I was looking at this going, yeah, you're going to need this for the midterm. If someone asks you what's a list, here's a definition of a list. What's the list? A list is an ordered collection, which allows duplicate elements. Its element indexes range from 0 to the list size -1. Because if you think about list starting with 0, and this is what you learned if you learned about arrays in the beginning. An array is a list, and those index values are the same thing as these index values here, or element items. So they do start with 0. Why? Because the number line actually starts with 0. So most people consider counting numbers, which starts with 1, 2. No one ever says, okay, 0, 1, 2, go! You go 1, 2, 3, go! So, long story short, it's not for humans, it's for programmers. So the list adds several methods for an ordered collection. So we have the interface. Remember those things called interfaces? Those interfaces that have templates of behavior, and we implement interfaces inside of classes. Okay, so the interface list is implemented by 2 classes that we have, and the classes are ArrayList and LinkList, and we saw both of these 2 last week. We both saw examples of both of those 2. They just add, what do they just add? They just add different features. They also have different running time. If you take an algorithms course, you'll learn about running time and efficiency of algorithms and big O notation and all that other stuff. I'm not going to bore you with that, because this is just a need-to-know kind of thing, or whatever you need to know is what you need to know. You don't really need to know the running time. However, they do have some efficiency differences. Adding and removing elements at the end of getting an element at a specific position is simple. Adding and removing elements in the middle might be more expensive for an array. This is why people don't like arrays, actually. In fact, in traditional style C++ programming, old style C++ programming, when you made your own linked list, you did that so that you'd have a better efficiently running algorithm versus and the linked list is here, but you don't have to make it, it's implemented for you. A linked list has a faster running time for inserting in the middle of the list. Because in an ordered list, in terms of an array list, you have to take every one of those items and make room for it. Move them all to the left, move them all to the right. You have to go through and you have to visit every single one of those items. So depending upon the size of the list, it increases how slow your algorithm runs. I should say that's kind of the backward way of saying it, but it makes the algorithm run slower the bigger the list, the slower running your program, essentially. And if you have like a huge database program, it may not necessarily be a good idea. So people would use a structure called a linked list, and a doubly linked list is one in which can be read both directions. So in C++, we always think of singly and doubly. Singly only has one pointer. So you have a piece of node, or you have a piece of data and a pointer to the next piece of node, piece of data and a pointer to the next one. That's a singly because it only gets read in one direction. Doubly has two pointers, the next and the previous. So you can read it forward, you can read it backward. The one that's implemented in Java is a doubly. Why not? Most people in C++ would implement it as a doubly as well. And believe it or not, you have these available too. You have built-in packages, actually they're called libraries in C++ and in Objective-C, that do the same thing as they do in Java. So it's just really old C programmers that probably were the ones who actually implemented their own linked lists originally. Now people just make an instance of the object, if they know object orientation in C++. Make an instance of that object, and I believe they call them templates or something similar to that, template classes, which is similar to interface classes actually. Interface template, well, what is an interface? It's a template. It doesn't have any implementation, but it has an outline or a template for the implementation. So you include the interface to include the functionality. So in essence, it is really the same thing. And so in the linked list example, the doubly list, getting the element at position I is more expensive. A good base for lists are actions that are not at the end of the list, because then you don't have to go to the end of the list. So something in the middle of the list cuts the list in half, essentially, in terms of the search space. So think of it more like a binary search versus, the efficiency of that versus a linear search kind of thing. But I mean, an example of using it is going to be that linked list, and what you've got essentially going on is looking at those examples I gave you last time, and then you'll see. Are you going to be able to tell the difference with those examples in running speed? No. They're all going to run the same. They're going to be insignificant. But when you have large chunks of data and you're working with big, huge data sets, then you start thinking about the efficiency of the list and the data structure that you're storing all the data in. Because how you store the data is going to determine how you're going to use it and how fast the access to that data or how efficient it's going to be. So we had the list. The other categories, the set and the sorted set. What I'm doing actually, that was slide number 10 so I remember, is going through this here. So I'm going to go through each list, set, list, sorted set, go through these items here on the tree so you can kind of get a good feeling for what these are actually. Back here. Here we go. So the set interface provides a more specific contract for its methods, but adding no methods of its own. It's just a set. A set is a collection that contains unique elements. So you can't put, in the list you can actually have items that are duplicate values. Because we're not keeping track of each one of the items by the item, we're keeping track of it by an index. So whether you use a linked list or whether or not you use a regular old array list, you can have duplicates all over the place. Set, you don't normally have duplicates because the item in the group is what's identifying it as being a member of the set. So if you have two items in the group that are the same, how are you going to keep track of which one is which? So the data structure itself does not lend itself to duplicate data. A set is a collection, of unique elements. So a sorted set extends the set. So what does that tell you? It's inherited from set. So set implements an interface set, and then we have sorted set, extend set to essentially specify additional contracts, additional iterators, such as a set will always return the elements in a specific order because it's sorted. So you're going to sort alphabetically, and you're sorting the items. You're not using an index. Instead, you're using the items themselves to sort the items. So if they're numbers, you could sort the numbers in ascending order, descending order, whether it's alphabetical words or something like that, names or people. So by default, it will be the element's natural order, which is determined by the implementation of comparable interface. So remember that comparable object? We used a comparable object. Okay, so we use an iterator to go through the list, iterate through the list. Comparable to compare objects. Is this one bigger than that one? Is this one less than that one? Does this one fall in the alphabet, lower or higher? So it compares. So we have a comparable interface that gives us less than, greater than, equal to, not equal to types of comparisons. So you can specify a comparator object to order the elements instead of the natural order. The natural order is going to be the way in which you put them in, actually. So if you put a list of names in and they're not in alphabetical order, the natural order is going to be in similar to that way that you put those in, depending upon what type of structure, how you got it set up, how you're putting them in. So there are two implementations of the set in the collection framework, and they are the hash set. We saw that actually. We saw a tree set, but we didn't actually print the tree set out. It just printed out tree. It turned a set into a tree set and then set the order, if you remember that example. But looked at that one. Well, how do we know that's a tree? Well, if you take a tree and flatten it all out, it's hard to see it's a tree. But essentially, you're going to use it for the order. And perhaps you're going to traverse it through, and you have an algorithm that's going to run on that tree. That's going to find the nodes or the paths through the tree. So the hash set is the set implementation using a hash table. Very efficient algorithm for those people who, going back to the C people, remember hash tables? So they're used for a lot of different things as another data structure that's kind of handy to know about because it's very efficient. Sorted, it's kind of a memory location using pointers, very similar to a linked list kind of example. The tree set is the sorted set implemented in a balanced tree structure, balanced or binary, sometimes referred to as 2 nodes per level, and then each level is balanced out, hopefully. And if you're not familiar with balanced trees or hash tables or anything like that, take a data structures course. You don't really need it for Android, or you don't need it for Java. You don't need it for anything really. So an example would be the hash set. And these are actually, I have one called linked list or similar, something similar to it. Take a look at the example called hash set. Actually, that's in that it's in that program that I compiled for you. Or excuse me, in that zip file that I made for you. Then we have the map and the sorted map. So the map interface does not extend collection. It comes from a different branch in the hierarchy. Because the map contains a key value pair. So it's a map like a dictionary, if you are familiar with the dictionary concept. So not only keys, but you get key values. So key value pairs, not only just the keys. Duplicate keys are not allowed in the map, obviously. So it's implemented by the class HashMap and TreeMap. So think of a dictionary. How many times does the word the show up in the dictionary? Once. How many meanings does it have? I don't know. Actually, maybe not. Shouldn't pick the word the. We should pick the word map. How many times does map show up in the dictionary? Once. How many meanings? About several different meanings associated with it. But it's all going to be grouped together in terms of values for that particular key. So you can have one key with several different values in a map, actually. It doesn't have to be. Usually, the old-fashioned dictionary was a key and a definition. Key and a definition. And then the map came around. It was key, definition, 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 definition. So theoretically, our dictionary is a map. It's a road guide to the English language, or something. Who knows? So there are methods to view the map using the collections. For example, here we have a key set. So we can set a key. We can set a key. We can go to the values, get the value of a particular key. So normally what we're doing is we're keeping associations. So we have a key with a couple of values, or one value, value 1, value 2, value 3. So the collection returned by the methods are backed by the map. So removing an element from one of the collections removes a corresponding key value pair of the map. Kind of like when you remove an item from the tree, unless you reorganize the tree, you're going to remove the whole branch on the tree. So in the collection, in terms of its implementation, you can override that, extend it, because everything is abstract, actually. You can create your own implementation of this particular concept and not remove everything, leave the keys. But, well, when you have an association, however, if you remove a key, you're going to remove the values that are associated with it. If you iterate through the keys in the value sets, you may return values from their respective sets in any order. The order is not known. It's sort of like a database concept, actually. It's a set. So there's no order in a set. There's no order in a database set either. So You can't just say, give me the order. You know, there's no order, so you have to create your own order to it. And put an iterator on there and assign some numbers or values to it. So the interface, SortedMap, extends map and maintains its list in sorted order. So we have SortedMap that takes a map and adds an index to it, essentially. And then we have TreeMap, which implements a sorted map. So we have map, SortedMap, TreeMap. And then we have your map, my map, her map, his map, all extended on it. So an example might be using hash map. There's an example actually that I gave you last week. So synchronized wrappers and the collections class. Synchronized wrappers. So I'll get some new vocabulary for you. So the collection class contains static utility methods, which can be roughly classified into two groups. Those are provided by wrapped collections and unwrapped. Unwrapped. So wrapped collections and those that don't wrap. And then what I'm going to do is run through some examples, and you'll sort of see what the differences are in terms of what these categories are. All the collections implemented provided by the Java util we've seen so far are unsynchronized. So concurrent access, and here's the thing. So it's like let's say for example we've got a database implementation, or we have a data set and we have it stored in one of these data structures. Well, what are we doing? We're accessing it. And maybe multiple users are accessing it. And if multiple users are not accessing it, there's no reason to synchronize anything, unsynchronize it all. If multiple users are accessing it, which is why we're storing it, if it's on the internet, and it's kind of like, think of it more like a database, actually. Databases need to keep track of what user came in, updated what user came in, changed this, queried on that, queried on this. You could do a query on something, and then the next 10 minutes someone can add something to it. You go to Fry's and you say, hey, I want to buy this. And then by the time you get to go find it, it's gone because 5 other people bought it. But the website said you have one, but it's gone. Yeah, oh, they're all gone because it wasn't synchronized. The website wasn't synchronized. It wasn't kept up to date. So when your data collections are being used, you're going to have the same similar issues actually associated with that. So concurrent access. If you don't have any concurrent access, you don't have to worry about any of this stuff. If you have concurrent access to a collection by multiple threads, could cause indeterminate results or fatal errors, because you might go update something that's gone. Someone removed the key. You can't add a value to a hash map when there's no key. So you're going to have issues that go on. And the keyword, let me just back up a little bit here on the keyword synchronized. For those people who are from C or C++ and who learned threadeds, p-threads, POSIX threads, threaded applications, you're in luck. You can throw away all that knowledge about threads. Throw it out the window. Now what we do is we synchronize. We can use the keyword synchronize. All of a sudden, it keeps the thread, everything runs as a thread out for you automatically. There's no more pointers. There's no more threads. Everything's operated, everything's controlled by the JVM. And so the JVM is doing your multi-threaded application development stuff. And in certain situations, you want to have a mutex or something like that, where only one thread is able to access the data set at one particular time. Because if multiple threads try to access it, you're going to have a race condition or a starvation condition and all that stuff you learned about threads and processing. If you don't know anything that I've just mentioned a few minutes ago, forget it. You don't have to worry about all that stuff. If you're brand new to programming and this is the first experience with thread, this is your thread lesson for today. Threads are running executions. So each object, this is the interesting part about Java actually, each object that gets instantiated creates its own thread, runs its own thread, which is interesting. And same thing that happens on the Android actually. When you make an instance of the activity object, for those of you guys who are in that class, it runs as its own separate thread in the JVM, and you don't have to worry, you don't actually have to synchronize anything in the Android environment because only one thread at a time runs. But in Java, on a PC computer or on another platform, when you have the JVM running, you have multiple threads running simultaneously. So you put the keyword synchronize next to the method. It says synchronize this method. That means play well with others. If another thread is using it, wait your turn. Or only, allow for mutual exclusion, or If there's a fatal problem, warn me about it, or keep track of something, or, synchronizing is sort of like the synchronized swimming, where all the arms are going and the legs are going all together. Well, it makes all the threads run together peacefully, essentially, when you use the keyword synchronized. So if you leave the keyword synchronize out, then you're looking at an unsynchronized, unthread-controlled environment. If you put the word synchronize on there, you're adding overhead to your program. It makes your program run a little slower because the JVM is keeping track of the thread and what the thread is doing, and it's hopefully going to prevent some errors that are happening. So in the use of these collections, we turn it on or we turn it off by the method that we select to run and the method that we select to implement. Instead of doing it on the actual running object, we're doing it on the functions that we're running inside of the object, the methods that we're running. We have some methods that are synchronized, some methods aren't synchronized. So we can pick and choose which ones we want to do. Here's some examples. Now I explain that. Let me go through the examples, and hopefully it'll sink in a little bit more. So the implementations by default are unsynchronized, so provided by Java Util. Concurrent access to a collection by multiple threads can cause problems. Obviously, starvation. They're both going for the same value simultaneously. Only one of them is going to update it. It's kind of like when two people open up a Microsoft Word document and they both make changes and they both save at the same time. Which one's going to save? Well, and you have to keep, someone out there has to be the traffic guard who's got to keep track of which one was first and which one was second. And then, oh, you can have it, or, split it or something. And that's what Synchronized is doing. And it's the JVM who's the traffic guard. Okay, so you can synchronize, so you can use a synchronization wrapper for those collections that might be accessed by multiple threads to prevent potential threading problems. What is the wrapper? The wrapper is the traffic guard who's gone out there and has taken the whole thing, synchronized it by wrapping it up, labeling it something, and keeping track of it. Is what all that means, essentially. It's like we've wrapped it with synchronization, which is where that terminology comes from. It's kind of weird. You have to imagine, you have to kind of think out of the box and imagine wrapping a method call with a synchronized behavior so that we can keep track of it. So methods in the collection class, to get synchronized wrapper, to get a synchronized wrapper, we call, and here it is here. Instead of calling a collection, we call it a synchronized collection. Instead of calling a set, we call it a synchronized set. And those are the implementations of the interfaces for set, in this particular case, that's synchronized. So in the implementation, each one of the method calls is synchronized, which means someone's going to keep track of what method was run first by which object, and hopefully your data in this particular structure is going to be more safe, more secure, less corrupt. There's still problems. In fact, you can still get locking situations where multiple threads are trying to access something and the JVM's not going to let it. So the whole thing just sits there and waits indefinitely. So, which is what the concept of starvation is all about. Nobody gets to use it because everybody's trying to use it all at once. So, sorted set, we have the synchronized sorted set, the list, synchronized list, map is a synchronized map. Basically, all you have to do is remember the word synchronized, add it in front of everything. You don't actually have to do this for any of your programming assignments for this particular course. Actually, you don't have to synchronize anything for your stock objects either, but you might actually think of the concept when you're looking at your stack and your queue. If you have multiple people looking at that stack and queue, at any one moment in time, the number of stock might change, and so it depends when you accessed it as to when that's going to change. If, for example, you accessed a method that was doing a count or a sort or some structure, and it was synchronized, and the method went out to go do it, to do the sorts or to go do the count, it would start back over instead of using temporary memory of what it happened the last time someone ran a sort on it, or it would actually start fresh. So what it does is it just doesn't keep any cache memory, no history, and it just pretends like, oh, this is the first time, so now, right now, in a moment of time, go out there and count it. So the count is always refreshed which is how the synchronization is working. Now, can you still get two processes that are trying to access the same piece of data simultaneously and both of them get wrong versions of it? Yeah, of course. It's not 100%. But it helps. It cuts down on some of the problems. So here's another synchronization example. The above methods return wrappers whose methods are fully synchronized, and so they are safe to use for multiple threads. Here's an example of a map where we have a map unsync map is equal to new hash map, and then we have a map sync map, which is a collection.synchronized map. We're going to send it the map, and we're going to synchronize it. So we basically put a wrapper on there. We put a synchronized wrapper on the map, essentially. So now we have the unsync map with a hash map, and then we have the sync map that's going through the synchronized wrapper that's also a hash map, and then we have elements that are inside of the hash map. And so the sync map has all of the relevant methods for the synchronized version of it, passing all calls through the wrapper map, unsynchronized map. And there's actually only one map, but there are two different views to the map. We have one that's synchronized, one that's not synchronized. And so the modifications on either map is visible to the other. So basically, synchronization also makes things visible. So one method knows when another method is actually updating something, and if something is updated, then it knows to refresh its whatever it has, not to count on whatever information it was previously keeping because somebody else has updated it. So we know we need to get updated again. So the wrapper synchronizes on itself, so you can use a sync map to synchronize access and then use a unsync safely inside such code. So here's an example of the synchronized sync map, taking the sync map, putting it into a synchronized method, and going through each item and updating it or putting it inside of it, keeping it inside of a different list, essentially. It's a list of the list, or a hash of the hash, essentially, that's keeping track of it. And then it knows when something has changed to go and refresh it, refresh the list. Unmodifiable wrappers on the collection class. So the collections class can contain a set of methods that return unmodifiable wrappers for collections attempting to modify a return set, whether direct or via an iterator, results in an unsupported operation exception. What does this make? Make it read-only. Unmodifiable, you can't write, but you can read to the collection. So you can use methods that are unmodifiable. What does that mean? Well, anyone knows of people who have taken and seen side effects from the use of arrays. Actually, this side effect, same side effect sort of occurs in Java sometimes. You know, an array is actually stored, and you send an array to a function does something, and then, oh my god, the entire function has changed my array. My array is now different than it used to be because of a little side effect, because of the way arrays are implemented. Well, because of the way some of these implementations are working, even though we don't have pointers, we're still working with pointers, and some values can actually be changed. So in C++, we have this keyword called constant. We put constant in there right after the function method, parameter to the function call, and then it makes it so that it won't change. Well, here we just call the unmodifiable collection. We use keywords. In fact, this is the same consistency that occurs with thread program. You want to create a thread, all you have to add the word synchronized to a method, and you've created a thread that's synchronized. So, and here we have 6 methods that return unmodifiable wrappers. If you use the unmodifiable wrapper and you try to modify, you get the exception. And I'm actually going to talk about exceptions today, so we'll see how those are thrown. So the contents of an unmodified wrapper can change, but can only go through the original collection and not through the wrapper itself. So as before when we saw that map, and then we had a synchronized map that was holding the map. So we create a unmodifiable collection that holds the collection, takes on the collection as a parameter. The collection is modifiable, but the unmodifiable collection is not. It's almost like saying, give me a read-only version of this right now, because I want to read it, I want to take a look at it, and then I don't want to accidentally change anything on it. That's what this is basically doing. It's like a substitution for the keyword constant, actually. So we can set the unmodifiable set here as a set. These are all the same examples over and over again. Sorted set, unmodifiable sorted set with a sorted set, unmodifiable list with a list, map with a map, sorted map of the map. Basically, you're going to take a collection and make it unmodifiable for your purposes of this collection object. So you're also making two objects instead of one, essentially taking the original object, making a temporary object out of it. If you think about it, it's sort of passed by value instead of passed by reference when you're using it, because you're using the value, not really the reference. Yeah?
So what is the use of declaring it unmodifiable? I mean, why would you
When you want to change it. Yeah, well, the reason that you're creating this data structure, this collection as an example, because you're adding stuff to it. Maybe you did like an internet search as an example, and you took all the things that you found and you stuck them in this collection. You know, maybe it was a set or something, sorted set of hit results. And you wanted to manipulate the results, but you don't want to change the results. So when you remove something from the collection, you know, and you remove this, remove that, take that out, oh wait a minute, I want that back. Can't get it back. But if you use the unmodifiable version of it while you're doing all that stuff, you haven't ruined the original collection. Because you're working on a copy. It's almost like making a photocopy of it and working on the photocopy instead of the original. You can do whatever you want with a photocopy. It's never going to change the original. It's a separate copy of it. But the unmodifiable version is not synchronized. It's unsynchronized. Because if you think about the concept, if you make a photocopy and someone changes the original, your photocopy does not get updated. It stays the same. But you can write all over your photocopy and make a mess out of it and then throw it away and make a new photocopy of the new one when it's available. So it's just a matter of being able to manipulate the set and sort of, photocopy is a flat piece of paper. Collection is, this dynamic thing that involves all this data and all this information that you're going to want to manipulate somehow. You're going to want to sort it, search it, find stuff in it, add something to it, take something away. And then you have to worry about, well, what happens if everybody else is using it? I'm going to permanently change it, so there's a need to have it unmodified sometimes. And we don't want things to happen permanently. So here's an example of the original. It's dangerous that an array's collection content can be changed. It is, and this is what I was trying to tell you before. When you create an array, you have the same problem with C or C++. Arrays are always passed by reference. Actually, all objects in Java are passed by reference, but we never make any. We don't use pointers, which is kind of weird. But it's a reference to an object. So it's going out into the object space, memory space that's reserved for that object, and it's automatically changing the contents of it. So arrays are objects too. And so if you make an array of suits and you go and you do something to it, you pull an item out, you do something with it, you're going to end up, accidentally changing it for, the next time you use that array, it's not going to have the same items in it. So using an unmodifiable wrapper, you can prevent the danger of actually changing the array values. So you've got this original array, but now you're creating a list suits. That's a collection dot, and running this method unmodifiable list. Array.asList suit names. And the suit names are all the names of the suit. These are cards, actually. Suit of cards. So you don't accidentally modify something and change the list. Because it could come into a really weird situation, especially, let's say you had a list of something and you accidentally removed an item from the list. And then it doesn't sync up with something else. Maybe it was a list of students and you got deleted from the student database, but you're still taking classes here, but you're no longer a student because you accidentally got deleted. And so whatever program was manipulating this data might go through and say, hey, invalid student. Wait a minute, what happened here? Because we were manipulating it, your registration and your payment and everything, somehow you got moved out or your name got changed or something. So the unmodifiable wrapper offers read-only access to others, as I mentioned before, while the read-write access is still available to the code itself, remaining in the object to the wrap collection, the original collection. So the original collection can still be used as the original collection, and then the unmodifiable collection, the wrapper that you wrapped around this collection, can be used whether you're wrapping it with a synchronization, and actually you can use both of them together. But why would you? You're going to use one or the other. You're going to use an unmodifiable wrapper to essentially make it read-only. But anything through the wrapper is read-only, but the original collection is still the original collection. It can still be used. It's kind of like when you take integer a and you have b is equal to a, but you can still use a. A is still out there, but a is the original. But b was equal to a, so eventually b is going to be outdated if you change a. So Abstract implementations. All right, so the collection framework provides a set of abstract implementations for you to design your own implementations of relevant collection interfaces to satisfy your particular needs. So now instead of extending, well, yeah, instead of, well, let me rephrase it. You can still extend, you can still implement interfaces and extend classes, and so you can still use inheritance. But you can also use the abstract version of all of these things instead of the original one. Why do you want to do that? Well, maybe you're going to completely override the entire behavior completely. Why extend it? Why extend the original implementation of it? Why go way up in the hierarchy when you can go down a little bit lower, get the abstract implementation, and then build upon that functionality? Is it going to give you the same end result? Yeah. So some people find it more flexible and easier to understand to work with the abstract implementation. But so a set of abstract classes. In fact, a lot of people just take the highest level, the sorted set or something, and don't even use the sorted part of it. Just create an instance of that object and use it. The only thing you get, though, and this is another efficiency kind of thing, not that we have to worry about memory these days, but if you're working on a small little embedded device or something like that, and you're running Java on it, like let's say an Android phone, and you're extending a huge class, whether you're using it or not, you're still implementing all of that behavior. You still have memory reserved for every one of those methods you may or may not necessarily be using. AKA, you get a big object out of that. Takes up a big footprint, takes up a lot of memory. Runs slower. If you go back down the hierarchy, take an abstract implementation, and for example, a set or a list in this example here, these are a set of abstract classes that you can implement, or extend, and then you can implement interfaces if you want to. But long story short, you're not getting everything, and instead you're going to specialize it so you're only using what you need to use, and you're only reserving memory for what you need to reserve memory for, and you're not getting a bunch of junk that's going to take up memory. And your abstract implementation eventually is going to create a smaller footprint on your object. It's going to make something that runs a little faster. So, which is why people pay attention to abstract classes. It's like, well, why implement it if you're not going to use it? And then sometimes when something is implemented, you accidentally use it. If it's not implemented, you can't accidentally use it. And in some cases, if you accidentally use it, it might actually give you unpredictable results that in the end make it a nightmare for you to try to troubleshoot, to bug fix this program, because it's working. Yeah, but when the sort does this, it removes all the items from the list. But why is it doing that? Because that's what the old implementation was doing, and we just inherited it, and we're just using it. But we don't want that, so then we override it. Then we have two methods there. We have the original one, we have the new one, and we have a new one on top of that. And then we have this object that's huge that runs kind of slowly. So, legacy collection types. We also support backward compatibility through legacy stuff. What is legacy stuff? This is actually coming from different programming languages. It's not necessarily legacy for Java. It's legacy for programmers in general. As an example, the old-fashioned enumerator. We don't actually have enumerators in Java. And anyone who's a C++ programmer, oh yeah, enumerator. Actually, it's a C thing, I think. It's not even C++. It's C. Where you take 1, 2, 3, 4, 5, and instead of having to remember 1, 2, 3, 4, 5, it could be red, white, blue, green, orange. And you have a color enumeration as an example, and you say, is color red? What did I start out with? Red? Oh, that would be 1. So it's almost like an array where the index values or integer values that are associated with colors that you're putting into the structure. Instead of calling it an array, you're calling it an enumeration. Well, what are you doing? It's just for iteration. So this enumeration is the analogous to the iterator. Because if you're an iterator and you're going through a list, you can go red, okay, next, white, next, blue, next. Does it have any more in there? You know? So it's supported in terms of that functionality. So the package Java util contains some legacy collections. Then actually it contains more than this list here as well, more than what I just showed you. They're still widely used in existing code and will continue to be used until programmers shift over to the new types. Yeah. Vectors. Vectors are still, in fact, in C++, vectors are arrays. Vectors are kind of still being used. Stacks, dictionaries, hashes. So that's why the dictionary is the map, but no one calls it a dictionary anymore. They call it a map. So I still actually prefer the word dictionary, but that's just because I'm one of those legacy programmers. So I'll never learn. Well, you know, when someone teaches you it's called a certain thing, you just kind of keep it that way forever, right? Well, I could check the time. It's 6 o'clock. Very good. Almost 6 o'clock. We're doing good. Expressions and I/O. I get through this today as well. So we'll be on time for GUI swing development on Wednesday, hopefully, unless I've forgotten a lecture in between. This is what I call the hodgepodge mix-match grab bag lecture. It's got exception handling and I/O and strings, I believe, in here as well. So why? Because these are miscellaneous concepts that don't really merit their entire lecture on their own. Instead, they can just be mixed into one. So here's an overview of exception hierarchy. Exception handling. Everybody loves that, right? It's not error handling, however. You know, error handling is a little different in concept. You know, when a user enters in a character instead of a number, that's error handling. When a method is expecting a certain value to be set and that value is not set so it can't make a connection, that throws an exception, which is where that terminology comes from, because the method is throwing it, not the user. So if you want a quick and dirty way of knowing the difference between exception handling and error handling, error checking is done by everything the user does, user's logic, traditionally. I don't know, you could probably grade the lines out a little bit here, and then exception handling is everything the program itself is doing. So we tell methods to throw exceptions when they're running, because if the method doesn't get what it needs to get, the entire integrity of the program is going to be thrown off. So we can stop the program and kind of deal with the issue at that particular point. So here's a simplified diagram of the exception hierarchy. We have built-in exception handling, just the same way as we have built-in thread processing and synchronization. Inter-process communication is built in, and we only have one word, synchronize, for that one. This one we have throwable is the top, so we throw something. It throws an exception, which is where that terminology is coming from. So we have throwables at the top. What do we have? We actually have two types of things. That's why I said we can kind of gray the lines between errors and exceptions, because they're both, we can have errors that are occurring within the code that aren't exceptions, and we have two separate categories actually. We have an error, which is just simply an error, and then we have the exception, where it could not necessarily be an error except for something went wrong. So it threw an exception. So exceptions, we have two different types. We have I/O exceptions, and this is primarily what you're going to be dealing with in your programs. And then we have runtime exceptions. A file. No, let me get into examples when we start talking about it, because I don't want to confuse you. Exceptions extend the class throwable. So now we extend throwable, which immediately splits into two branches, error and exception. Error, internal errors and resource exhaustion inside the Java runtime system. Little can be done with errors. If the Java JVM runs out of memory because your collection is too big and you've extended off of the largest class you could possibly find in the hierarchy, and you've made one small little thing out of it, and you've made dozens of them, and you've taken up a lot of memory, you will actually, there are programs that run out of memory. There's nothing you can do about it. It throws an error. The error actually goes out into the runtime, and you'll see the error written on the screen. Actually, there's a nice little error when you write a program that doesn't include main. There's your first error. It goes, I can't run. It's impossible for me to run. There's no main. So it throws an error. And the error is written out on the screen. It says Java error number blah 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 blah. And then it usually tells you, main something or other missing. I can't remember. You can easily throw your own error there. An exception splits off into two branches. The exceptions are either I/O exception or the runtime exceptions. And then we have different variations of those two. So the two branches here. Exceptions that are derived from runtime exceptions. Actually, I believe that error is a runtime error. No, maybe not a runtime error. I don't know. I haven't seen that error in a while. Can't seem to remember. Examples: a bad cast, an out of array access. You put 5 items in an array and you go for the 6th. In C++, you don't get anything because they don't have built-in exception handling. In Java, you do that, and the program says, "Wait a minute, there's only 5 items, and you're going for number 6." It's going to throw this runtime exception on you because during the runtime of the program, it came up with that error, which is a benefit. So this is why, going back to the comparison between C++ and Java, this is why people actually think Java's safer, which it is actually, because as a language, you can actually, it catches stuff like this. In C++, if it doesn't throw a problem, it just writes into some memory address that it doesn't belong to that array. It reads it, and you get garbage, and you get some sort of a really weird effect that happens. You know, like the value turns into null or something happens with the logic of the program because it didn't catch an out-of-array access. Happens because errors exist in your program, they're your fault. Runtime errors, exceptions. Then those are not in the type of the runtime exception. Example, typing to open a malformed URL. Trying to open a malformed URL. Well, that's going to be a problem if it's not formed correctly. The program is good, but bad things happen. Not necessarily your fault unless you've hard set that URL. So it usually comes from the runtime environment in terms of errors that occur, not necessarily exceptions. So checked exceptions versus unchecked exceptions. By default, nothing's checked. You have to add, in fact, all the programs you've been writing so far have no exception handling. Nothing. We haven't even looked at this yet. So unchecked exceptions, exceptions derived from the class error. Let me hold back 1 second. We haven't been doing any exception handling, although errors are handled. I don't want to confuse you with that. We haven't thrown any exceptions to fall into one of these two categories, whether it's going to be checked or unchecked in terms of the exception. You'll see in a few minutes what I'm talking about. Okay, so unchecked exceptions, exceptions derived from the class error or the class runtime exception. And checked exceptions are those that are not unchecked exceptions. If they occur, they must be dealt with in some way, hopefully. A compiler will check whether you provided exception handlers for checking exceptions which may occur. So basically the unchecked exceptions are the ones in which it's an exception that occurs, but you don't have a handler built for it. It's unchecked by the program. So it's the runtime environment that has to deal with it. Runtime environment is going to come back and say, was there anything there? And here's where you can just put a generic throws exception. And then it just catches anything that happens. And then you can use it for, I don't know, error checking, debugging your program, whatever. So declaring a throws checked exception. So here's the checked categories. If we're going to check it, we have to throw something in order to check it. So it's like a throw catch. It's kind of try catch if you think of it that way. It's kind of a try catch, but we're throwing it instead of trying it. We can actually use try catch in Java as well. And if you're not familiar with that, don't worry about it. It's a C++ thing. Because we don't have throws. We have something similar to it in C++. In C, you have try catch. You try to open a file. And if the file doesn't exist, you catch a file not found exception, and then you deal with it. So Java methods or constructors should be declared to throw exceptions under two different situations. In situation number 1, I wonder why this showed up in blue. Interesting. It calls another method that throws a checked exception. Okay, so it calls a method, throws a checked exception, so this one has to throw an exception. Otherwise you get an error actually. If you're calling a method that throws and you're not throwing, then Java will come back and say, needs to throw the exception. Would you like to add it in there? Actually, Eclipse will do that, and then it'll add it in there for you. It throws a checked exception with the throw statement inside its body. So when you make the method, you can throw it. Or inside the body, if you're not going to do it on the method, inside the body you can throw the exception. You're like, okay. So here's an example of a single exception here, where we have public file input stream, and here's our string s, throws file not found exception. This is on the method. The method is going to be file input stream, and it's going to take a string, a regular string variable as a parameter. And it's going to throw a file, and files are strings actually, by the way. Well, we're going to talk about, this is why we're doing IO exceptions and strings all in the same lecture, because they're kind of related in terms of exception handling. When you're opening and closing files, you have to throw exceptions. Otherwise, you'd have programs that run away. Couldn't open the file, but it kept running, even though it wasn't saving any data. So, multiple exceptions, you separate them by commas. So we have maybe a load on this one throws an end of file exception and an IO exception. Instead of throwing a file not found exception. And you're probably at this point going, how many exceptions are there? I'm going to show you a slide at the end here that's got like a dozen of them on there. And here's where you go out to the internet, or you go out to a book. It's something like, how many exceptions are in this category? How many are in that category? What are these exceptions? And then you figure out what they are, and you basically use them all over and over again for the same situations. Most of them is for file I/O. You should not declare an unchecked method after throws. They are either outside of your control or should be avoided completely by correcting your code, because once you've thrown, you shouldn't actually have to declare anything, because it's already being checked because of the throws that you've put on the method. Using throws to throw an exception. Here's an example. Hopefully I've put all the pieces together. So throw an exception under bad situations. Here's an example, a method named readData. And here's our readData method here. It's of data type string. So the entire method here will be, it's written right here actually. So readData is reading a file whose header says it contains 700 characters. But it encounters the end of file at 200 characters instead of 700 characters, which means it didn't read the entire header correctly for some reason. Who knows, maybe the file's corrupted, or maybe you get the wrong file. So you decide to throw an exception when this bad situation happens by using the throw statement. So here you go, throw new IO exception. You can do that inside the method body, right when you're opening up the file and doing something. Or you can do it this way, where you have end of file exception E. So you're making an instance of that object, end of file exception. And it's going to be equal to an new end of file exception, and then you're going to throw E. And you're going to put the entire method, you're going to put it inside. So down here we're going to use this first one up here instead of the second one. This is more common actually, because this is more typing. So two ways of creating, and what you're doing is you're creating an exception object, or you're saying throw and create this object when you throw it. Either way, the object has to exist, whether you create it now or whether you create it once the problem occurs and you have to throw the exception. Because the exception object, just like all other objects, is there for a reason. It keeps all of the information. What line of code were you on? What happened? What did the runtime say about this? Who you are? What time of day is it? All this information that's stored in the methods, the gets and the sets of all the data that this exception object is keeping track of. And hopefully the exception object will say, hey, I only have 200 characters, don't have 700 characters or something in this particular case. So you string, here's the string data, this is the method here we're putting, and this is the method on the method declaration line. We're saying throws an end of file exception. We have some code while something happens. If n doesn't have next, end of file occurs. And if n is less than the length, so n was like 200, the length was 700, then throw this new object exception here. And new object exception is going to pick up this information and provide you a way of, once you throw it, you have something to do with it. You can print it to the screen and say, hey, I only got 200 characters when I really needed 700 characters or something. So using throw to throw an exception to continue in the concept here. If the method body can only throw exceptions, which are the same type or the subtype of the exception declared after throws in the method header. So in the method body, you can only throw the same type of exception. So this guy here, end of file, if you're going to use this approach, if you throw in the method body, if you throw in the method declaration end of file exception, you're throwing inside an end of file exception in here. Because you're using throws have to, basically they have to match. So it can only throw exceptions that are the same type of the subtypes of the exceptions declared after the throw. So in this particular case here, we've got two of them, end of file and IO exceptions. We can throw both of them inside the body, which is why you're listing them out. Sort of think of it sort of like when you abstract or you inherit, when you implement an interface, you have to list all the interfaces, otherwise you don't have it inside of the method. Inside of the class. If you can find an appropriate exception class in the library, you can make an object of that class and throw it. So you can throw another object of a difference as long as it's appropriate. Otherwise, you design your own throws exception class. You can create your own throws exception class. So creating your new exception types. Here's an example of creating your own, and you're basically creating your own type. Exceptions are objects, as I mentioned before. They hold information. They have functionality to them. You can print out the exception, to string. You can send it somewhere. You can have it do something. New exception type should extend exception or one of its subclasses. So if you look at the hierarchy, you can go, well, we can throw runtime exception, IO exception, end of file exception. So when you say my new exception extends IO exception, and you've made a new object, you can throw your new object. And it's compatible with, if you remember this whole object compatibility thing, it's compatible if you used EOF, end of file exception inside, and you extended from that, well then it's also an instance of that object. So it can be thrown with an end of file exception on a method call. Why creating new exception types? Why are you going to do this? You're thinking of this, I'm never going to do this. I never have to do this. As soon as you start opening and closing files, you're going to want to do this. Otherwise, you have no way of controlling what's going on with your program. Your program becomes unreliable. All right, so describe the exceptional condition in more detail than just the string that exception provides. How many people have actually looked at the runtime exceptions that come out? Well, let me rephrase that. If you've been doing any of the assignments for this course, you've compiled and you've run a program. Unless you're a genius, you're going to get some exception that's going to show up on the screen. If you don't like the way that those look, you can rewrite them. Include your own method, your own message that says, hey idiot, you forgot to do something, or something of that nature. Suppose there's a method to update the current value of a named attribute of an object, but the object may not contain such an attribute currently. Doesn't contain it, but it doesn't have it, but you're trying to update it, and it's a named attribute of the object. You want an exception to be thrown to indicate the occurring of the situation. So you want to say no attribute name such and such found. Because if there's no attribute, how can you update an attribute that doesn't exist? So this would be a nice one. Instead of saying, hey stupid, no attribute named something found. Actually, you can have it say whatever you want. When this exception gets thrown, when you extend this and you include no such attribute extension, it will print out your customized message that you've overridden from the original exception that you actually overwrote. So you're going to throw this object, no such attribute exception. And this is a classic inheritance. This you should be familiar with at this point. So this is public class, no such attribute exception, extends exception. This is just like public class student who extends person. Same thing. We have public string attribute name, no such, and then inside we have this method here. It says no such attribute exception is constructor, takes on a string name, and the string name goes back up to super because it's from exception. Super would throw out that message, so the super constructor that takes on the string name is now going to print out no attribute named such and such attribute name is equal to name. I don't know, the name is just going to be some name that you basically made. So you're going to create the attribute from that. So the type of exception is an important part of the exception data. Programmers need to do some actions exclusively to one type of exception condition, not others. So it's a way of customizing something so that you can actually get some more meaningful error messages that appear on the screen. So we've talked about throwing them. Now we have to catch them. So it's like throw and catch. Catching exceptions. Checked exception handling is strictly enforced. We always catch the runtime environment takes care of it. If you invoke a method that lists a checked exception in its throws clause, you have three choices. Number one, catch the exception and handle it. So you have a catch clause and you handle it. Two, declare the exception of your own throws clause and let the exception pass through your method. You can have a finally clause to clean up first. So you can actually declare the exception of your own. So you can go back to that previous example, extend the class and do something to catch it, to deal with it when it happens. Put your catch in there. And let the exception pass through your method to let it process somehow, and then clean it up. Catch the exception and map it into one of your exceptions by throwing an exception of a type declared in your own throws clause. So throw an exception from the exception. After you've caught it, throw an exception from your personalized throws exception. Or use try and catch. So here's the try catch clause. Basic syntax of the try checked is the same as C or C++ actually. If you're familiar with try catch in the past, try something. Catch, 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 catch. When are we catching exceptions? So we're going to catch exception type 1, exception type 2, and then if this happens, do this, if that happens, do that kind of thing. So if no exception occurs during the execution of the statements in the try clause, it finishes successfully and the catch clauses are skipped completely, nothing ever happens. Try this. Okay, it worked. Forget about all the catches. If the code in the try block fails, throws an exception. So we're still throwing an exception, but this is how we're catching it. And this is an example of number one, catch the exception and handle it. So what I'm going to do is go through these three methods. The first one is catch it and handle it. Catch and handle it uses try catch. We're still throwing it in the old traditional pattern, but inside the method we're trying and then we're catching. Because it makes no sense to throw an exception if you're not going to catch it. I mean, it's going to be out there. Otherwise, you're going to have the Java runtime environment print out some crap for you and do some weird stuff for you. Or it might even continue, actually. You can throw it, print it out, and continue going if it's not fatal. All right, so if the try clause fails, something fails inside, then an exception is thrown, either directly via the throw or indirectly by the method invoked inside of it, because you can invoke a method to throw inside of it. The program skips the remaining of the try block, stops exactly. This is the same behavior as you get in C or C++. Stops where it finds the error, automatically goes to the catch, finds an appropriate catch or a default at the end. If an appropriate catch clause is found, the code inside it gets executed, and the remaining catch clauses are skipped. It's like a case switch with breaks in it. Actually, it doesn't go to the rest of them. If no such catch clause is found, then exception is thrown into the outer try, and might have a catch clause to handle it on the outer, which is kind of the default. If you think of it, if you develop a default. Otherwise, if you have no outer catch try, you're not going to have anything caught. The catch clause with a superclass exception type cannot precede a catch clause with a subclass exception type. What does that mean? Well, you have a throwing an exception inside, you're throwing another exception inside there, you got another clause in there. It goes inner to outer when it gets caught. So you always get the inner one that will execute. The outer one won't go until the inner one goes. It kind of makes logical sense if you think about it. Depends on where you're operating in the code. If you haven't reached that part of the code, obviously you don't have to worry about it. The outer one's going to execute. because you don't have any inner ones to actually work with yet. Which is why you get all of the, if you're ever looking at any of the error messages that come out of your failure to run program, your program that, my beautiful program that I created and I ran it and I got all these error messages that showed up, only look at the first two or three. The rest of it is garbage. Because it's the first couple of lines that show up that hopefully haven't scrolled off the screen that is what the real problem is. Everything else is just a consequence associated with the runtime exception handling is going to catch everything, inner to outer. So it's going to give you irrelevant stuff towards the end when all you have to do is fix the array index. But you're going to have all stuff about main and the object and the method and all this other stuff is going to come out of it. So, which is ridiculous because they should just print out that one little line instead of printing everything out. So here's an example. So let's see it done from a programmer's perspective. We have public void read. Read is taking in as a parameter line a file name, string. It's going to try, and it's going to input input string in, which is going to be equal to a new input string file name. And then it's going to read here. So the read method below is one that will throw an IO exception. Let's see. This one's going to throw an IO exception. If it doesn't equal -1, well, it's not going to equal it. Process the input. Well, it can't process the input. So b is equal to in.read. So catch the IO exception E, and then the exception is going to be a print stack trace, which is a method on the IO exception. This is what I was saying. You have these methods that the object's holding. One of them is going to be the print stack trace, which is going to give us all the problems it came up with. A log, essentially, of all the error messages that occurred. So another choice for this particular situation, and this is the C++ kind of way of doing it. Putting the try in here, putting some code that's going to fail. This code's going to fail, and it's going to catch this exception, and then we're going to, from this exception object, we're going to print out the print trace. So another choice to the situation is to do nothing, but simply pass the exception onto the caller of the method. So send it back to the method that called it. So you're going to send it to the outer instead of dealing with it from the inner perspective. And here we have the read throws an IO exception. Oh, okay. So this is throwing the IO exception up here on the method line, brings it out to the method. This is inside of the method, it's dealt with inside of the method. This is outside of the method. Anything that happens inside is going to go back out to the outside of the method, and whatever called this method is going to come back and says, hey, we threw an IO exception. So the calling party is going to have to deal with it, essentially. I sort of prefer this method, actually, deal with it inside of the method. Then I know exactly where the problem occurred. Because if I call the method from another method and the other method fails, because it gets an IO exception, where in the world did the problem occur? This is closer to the source of the issue. This is farther away. This is harder to implement. This is easier to implement. So, more time. Oh, is it time? Okay, so I'll end at this point here. Is it 5:20 or 5:30? Or 6:20. Okay, good. Okay, so if you call the method from here, if you call the method and throws a checked exception, you must either handle it or pass it on. So check the API documentation to see what exceptions will be thrown. So anyway, just remember you have two ways of catching it. One's from the method itself or one's from inside of the method, depending upon where you want to deal with it. So I'm going to stop this lecture because I want to talk about assignments and stuff. So I'm actually going to stop the video as well.